On the board, I've given us a problem. Find the differential of the function. A lot of the homework's going to say this, and you'll notice I'm not given a specific point. I'm not given values for dx and dy. So this is just asking me to find a formula for the differential at an arbitrary point, given an arbitrary amount that I'm going to change my variables. Okay. So, in general, if this function was spitting out, I guess it would probably be a z value. Okay. I would say that dz is just the gradient of f dotted with dx dy. Okay. Notice that's just going to be the partial with respect to x, partial with respect to y, dotted with dx dy. So that's just f sub x dx plus f sub y dy. The partial derivative with respect to x times dx plus the partial derivative with respect to y times dy. And that's encapsulating what we talked about when we were first talking about building this candidate for our tangent plane. And that's a rate of change of z with respect to x times an amount that x is going to change. A rate of change of z with respect to y times the amount that y is going to change. Now, I do have to do a little bit of work here. I don't have specific numbers to plug in, but I do have a formula, so I can calculate the formulas for those two partials. So, let's see. Partial with respect to x would be a negative sine of x squared y times the partial with respect to x of x squared y is 2xy. I sort of left some space for that a minute ago. Dx. Plus, the partial with respect to y is going to be a negative, so I'm just going to write that as a minus. It'll be another sine of x squared y times x squared, and then that gets multiplied by dy. All right. Now, if I look at this differential for my function is essentially a function now of 4 variables. Because I have x and y, those are 2 variables that would indicate a location. That would be where I was going to calculate my linear approximation. And then I've got dx and dy, those are variables that would represent the amount that I want to move away from that. Okay. So I just wanted to point this out, because here's an example of a function of 4 variables, but I don't have it because I want to do a graph in 5 space. I have it to help me understand a little bit better this function whose graph is in 3 space. I just have 2 variables to tell me where I am and 2 variables to tell me how much I'm moving away from that location. Okay. So let's actually go ahead and use this. So let's use dz to approximate delta z if xy is, let's just go with 1 pi, and dx is 0.01, and dy is 0.02. Okay, so in that case, I've actually got some things to plug in for all 4 of those variables. Okay, so let's see. Negative 2xy, that's going to become negative 2 pi. So we would say delta z is approximately dz, which in this case would equal negative pi times sine of pi. Oh, that's not very interesting. Let's change this to pi over 2. So that we don't just get 0 for everything. It's perfectly acceptable to get 0, it's just boring. Okay, so I'm going to change my y value to pi over 2. That's a little more exciting. Okay, so then we've got negative 2xy is just negative pi times sine of x squared times pi times y is going to be 1 times pi over 2. Sine of pi over 2 is 1. Okay. Dx. Oh, and we're plugging in for dx. What is dx? 0.01. Minus x squared is just 1. Sine of x squared y, we said was sine of pi over 2, which is 1. So we're getting just 1 times dy is 0.02. Okay. So we've got negative 0.01 pi minus 0.02. Okay. Now, of course, if I'm approximating things, I would probably then approximate pi is about 3.14. and then come up with a decimal approximation of things. But I'm going to go ahead and just stop at this point.